Alright, let's take a look at problem number 11. Go ahead and read that to yourself. Feel free to try to solve it on your own if you like. Pause the video as you do so. Come back to see how I do it. Or if you get stuck, come back to see, maybe get some hints. Alright, this is a problem that's quite pertinent because it happens all the time that students just accidentally knock things off their desk. And I actually did measure the height of the desks in our classroom, and they are 73 centimeters tall off the ground. And so this is, like I said, a very pertinent sort of problem. It's good to know these sort of things. Alright, first thing you want to do is realize that everything in this problem is going to be vector quantity. So the first thing you want to do is establish a positive direction. Well, first let me just go ahead and I'm just going to label 73 centimeters on the picture here. That is the height of the desk off the ground. But the next thing we want to do is we want to label a positive direction. And so the best advice I can give you for labeling a positive direction is to establish the initial direction of motion, or the eventual direction of motion of the object. In this case, knock it off, so initial velocity is 0, which means it's going to be falling down. So I would call down the positive direction. So we can do that just by putting an arrow with a plus sign next to it. Now in the end, you can actually identify whatever direction as positive that you'd like, and I'll even show you what would happen if you were to do that. But I just find most students really like this idea of initial direction motion as being the positive, and we'll explore why in a little bit. Okay, first thing we want to do is find it's time to hit the ground. There's all sorts of ways to go about doing this. All sorts of kinematics equations you can choose from. Some students may in fact go out of order. Some students may find the velocity first and work backwards to find the time. There's absolutely nothing wrong with that, but the solution I'm going to show you is going to be in the order here, and there is a particular kinematics equation that's going to be able to do it in one shot. I wonder if you were able to find it on your own. If not, well, here it is. It's going to be this one. Delta y equals v naught t plus 1/2 at squared. Now, first thing is you might notice that I switched from delta x to delta y. I like to do that when we're dealing with vertically moving objects, but you want to leave it as delta x, that's fine. If you even want to leave it as d, like we did in the summer assignment, that's fine as well. But I like to call it delta y to remind myself it's going vertically. Why is this a good equation? Well, we know what the delta y is, right? We know it's going to fall 73 centimeters, and we know the initial speed is 0, and we know the acceleration. Now, the acceleration is not given the problem. How do we know what that is? Well, what happens when you knock it off your desk? What forces are acting on it? Hopefully you realize it's the force of gravity, and assuming there's no air resistance, that's it. It's just the force of gravity. Now, how do we know we're supposed to assume there's no air resistance? Well, it's because we pretty much always assume there's no air resistance. The problem doesn't have to tell you to do that. That's just always the assumption. The problem would actually have to go out of its way to tell you if there's air resistance to contend with in the problem. So just always assume things are done in a near vacuum or in a situation where air resistance is pretty much negligible, in which case if it's the only force acting on it is the force due to gravity, that means we're in free fall. If it's in free fall, that means we know the acceleration. The value is going to be 9.8 meters per second squared, and it's going to be accelerating down. So we know those values. We know what delta y is, we know v naught is, we know what acceleration is. That means that we can solve this for time. So since the initial speed is 0, and anything times 0 is 0, I'm going to cross off that whole term, and then, as always, we want to rearrange first, algebraically, before putting numbers in. So if you haven't done that yet, either do it in your head or do it on your paper. Right, so we're going to rearrange this, solve for time. And hopefully we should be getting 2 delta y over a, take the square root. Now, yes, you could have delta y over half a, take the square root, nothing wrong with that, but really, no one likes fractions in the denominator, right? So I would move the 2 over to the other side first, divide through by a, take the square root, or divide by 1/2, which makes a 2 in the numerator. Either way, I think is the easiest way to look at it. Alright, so now we're just going to go ahead and put our numbers in. We know that delta y is going to be 73 centimeters, and again, the acceleration is going to be 9.8 meters per second squared, because we're assuming this is free fall. Notice I left some blanks there because everything here is a vector, which means we're going to have to put a sign on these terms. So let's look at the displacement first. All right, the 73 centimeters. Will that be positive 73 or negative 73? Why don't you just go ahead and pause the video and think it through for yourself. Okay, so it's not really a guessing game. You should be able to figure this out by figuring out which way the object is moving and which way we call positive, because that is what we did, right? We decided to call down the positive direction, and the calculator moves from here to there. So the displacement vector points down. So if the displacement is down, and we call down the positive direction, that means that the displacement is going to be a positive amount. So we're going to put that sign there, positive 73 centimeters. And so this is a question that's going to come up throughout the entire year. What sign does the vector get? And it's never a guessing game. It's really just a matter of comparing whichever way the vector points to whatever you call the positive direction. So let's try this for the acceleration. Should this be a positive or a negative 9.8 meters per second squared? So again, pause the video, think it through for yourself. How do we answer the question? Well, we just look to see what do we call the positive direction and which way does this vector point. this vector is the acceleration vector. Some students say, oh, it's going down. Well, you're right, it's going down, but the word going or moving, that's associated with velocity. Is the calculator going down? Yes, it is. Is that what we're looking at right now? No, it's not. We're looking at acceleration. Let's be really, really careful here, because we want to know which way the calculator is accelerating. So we know when you let go, of course, the force due to gravity is pulling it down. It's going to accelerate down. And so the acceleration vector points down. That's really what we want to focus on here because that's what's in the equation, right? So the acceleration points down, and we call down the positive direction. Oh, okay, so if down is positive and accelerating down, that means that the acceleration here is going to be a positive 9.8 meters per second squared. That's how you figure it out. Compare the direction of the vector to the direction that you decided was positive. Okay, so now we can go ahead, crunch our numbers. Go ahead and do that if you haven't yet. Let's see what we get. Okay, so if you just do the numbers I have up here on the screen, you're going to get 3.9 seconds. Okay, some of you got that. Some of you may have gotten something different, and let's talk about what may have happened here. But first, let's just think about 3.9 seconds. 3.9 seconds, that's almost 4 seconds, right? So again, this being a pretty real-world sort of problem, imagine yourself sitting there at the desk. You knock your calculator off the desk. So in your mind, as you're visualizing this, is the calculator going to take 1, 1,000, 2, 1,000, 3, 1,000, 4 seconds to hit the ground? Does that sound reasonable? It doesn't, right? Because, look, if your calculator, which I'm sure you paid a lot of money for, those expensive graphing calculators, whatever they are, right, takes 4 seconds to hit the ground, then, well, okay, if you knock the calculator off your desk, you got plenty of time to, even like in like a slow-motion Matrix style, swoop down and catch that calculator before it hits the ground, shattering into all those pieces. But that's not what happens, right? Your calculator falls very, very quickly. You don't have time to catch it, and then you got to go home and explain to your parents why you need a new calculator, and maybe you have to do some extra chores to pay for it, because those calculators can be rather expensive. So there's no way 3.9 seconds makes any sense. That doesn't agree with our real-world experience. So what happened here? Well, hopefully all of you, or if not all of you, most of you figured out something went wrong with the units, because 9.8 is in meters per second squared, and the displacement here is in centimeters, and we can't mix and match those, right? Hopefully you all caught that. If not, well, you really got to be paying attention, right? It's not just a matter of putting numbers in the equation. That's math. This is physics. We have to make sure everything's lining up, and our units have to agree. So let's just do a quick unit conversion, converting 73 centimeters into meters so they match. And you can certainly do it on your calculator if you like to, or write it out if you have to, but that's the sort of, conversion you should be able to do in your head. Going from centimeters to meters has to be pretty quick. And so we should recognize that 73 centimeters is the same as 0.73 meters. So now go ahead and crunch the numbers again if you got it wrong the first time. Let's see what we get this time. And now we should be getting 0.39 seconds. And that's a number that makes a whole lot more sense, right? Less than a second, because human reaction time is usually about 0.2 seconds. And so it's going to take you a little bit of time to recognize you knocked off your calculator, and then only 0.4 seconds to reach down there and grab it. And that's why you probably won't be successful actually catching that calculator before it hits the ground. It only takes about 0.4 seconds to hit the ground. That's a number that makes sense. Now, when doing this, again, we called down the positive direction, but I did say you can actually call whatever direction positive makes sense to you. So let's just think through what would happen if instead you called up the positive direction. Okay, let's go through them one at a time. So now we look at the displacement. So no matter what, the calculator, it goes down, right? So the displacement vector points down, but if you call up the positive direction, then the displacement would be negative 0.73 meters, and that's fine. What about the acceleration? Well, again, no matter what, it's going to accelerate down because the acceleration due to gravity points down, but, we called up the positive direction. So if the acceleration points down and up is the positive direction, that would be a negative 9.8 meters per second squared. And if we have a negative 0.73 over a negative 9.8, those negatives will cancel, and everything's going to be just fine. You're going to get the exact same answer. The problem would be if you're not consistent with your signs. So if you assign your positive direction and you get one of the signs correct and the other one wrong, well then one of these will be positive and the other will be negative, and then you're going to have to take the square root of a negative number. Now, you should have learned before, but if not, I'm going to tell you, you can't do that. You can't take the square root of a negative number. In fact, feel free to try it on your calculator right now if you don't believe me. And calculator won't do it. It's going to say error or syntax error or make a frowny face at you or start calling your mother nasty names. The point is, it's not going to do it because it doesn't exist. You can't take the square root of a negative number. It doesn't have any physical meaning to it. So, why am I saying all this? Well, it may happen at some point that you're doing some problems and you end up with an unexpected negative sign under a radical. you may be tempted to say, oh, I'm just going to throw the negative sign away and hope for the best. Well, I'm going to warn you, don't do that. Because if you ever get a negative sign under a square root, it's telling you something went wrong. It may be as simple as you messed up with the sign convention and go back and figure it out and rethink it. Other times, though, in more complicated equations, it may mean you actually did something mathematically wrong, crunch the numbers again, or something went wrong somewhere is the point. That you can't just throw the negative sign away, put the number back in, take the square root, because, well, one, conceptually you did something wrong, but two, it may actually mean there's a deeper problem in your solution. Plus, if the solution were presented to me on a test or to the grader on the AP exam, and they see you just threw the negative sign away and you didn't fix it, well, guess what? We will see it, and you're going to lose points anyway. So the point is, if you ever get an unexpected negative sign, it's up to you to find the mistake and fix that mistake. Let's go on to part B. Part B asks for its velocity as it hits the ground. Now notice the wording there. It doesn't say its velocity after it hits the ground. I think we can all agree after it hits the ground, it's not going to be moving at all, so the velocity is going to be 0. But that's not what this problem asks. And we are asking for the velocity at the end of the problem. We're looking for a final velocity, but it's the velocity as it's about to hit the ground, not afterwards. Because afterwards, it's not even in free fall anymore. That's not useful to us. We want to know its velocity as it's about to hit the ground. So we are solving for VF, but VF is not going to be 0. Okay, so at this point, if you haven't done it yet, go ahead and pause the video and try the problem on your own. Now again, some of you may have actually gone to part B first to work backwards to find part A. Nothing wrong with that at all. And so some of you may have already done this part, but for those of you who haven't, well, you have some options here. We have a couple different kinematics equations that we can use. We can either use VF equals V0 plus AT, because we just found the time to hit the ground, or we can use the time-independent kinematics equation, solve for VF by taking the square root of both sides, because we have the displacement as the 0.73 meters. Either way, we know that the initial velocity is 0, so V0 is going to cross off for either of those, and no matter which one you use, you're going to get something very, very similar. But notice the problem does ask for velocity as it hits the ground, not speed as it hits the ground, which means we're looking for maybe a little bit more than you've already answered. So maybe just pause the video and think through what is necessary to have in your answer to give a complete answer here. Since it's asking for velocity, not speed, it's not just the magnitude, we need the direction as well. There's all sorts of ways to go about that. No matter what, when you put the numbers in, you're going to get a magnitude of 3.8 meters per second. But notice I also put the plus sign on there. Why did I do that? Well, that's going to give direction. Now that we've established down as the positive direction, we can use that plus sign to indicate direction. So we can now box this in as our full answer as positive 3.8 meters per second. You're going to get the same answer regardless of which equation you use, but no matter what, you have to put that positive sign on. Now some of you may say, well, isn't the positive sign implied? In math it is, and sure, in math it is. But this is physics, which is not the same thing as math. And in physics, if you need to give direction in your answer, you need to give direction in your answer, which means there's probably going to be a point attached to it on a test or on the AP exam. And so if you just leave that blank and say, oh, it was implied, well then guess what? You're actually going to be giving away a point. So don't do that, right? So just take the extra fraction of a second and put the positive sign in front of it. Now, if you got a negative answer, just leave the negative sign in front of it. That's going to answer the direction as well, because it'll just be opposite to whatever it is you decided was positive, and that's absolutely fine. If you don't want to deal with any of this, you can just put the word. You can write 3.8 meters per second down, because of course it's moving down, so the word down would give direction. So it's just either or. Either put the sign to indicate direction, or put the word. But just be very aware that if the problem asks for direction, and you want to use the sign, you really have to do two things. One, you have to put the sign, and two, you have to explicitly tell your grader what you're calling the positive direction, either in words by saying down is positive, or doing as I've done here by putting an arrow with a plus sign, in this case indicating down is the positive direction. Alright, what about that last part there? What if instead of it being your calculator, what if it's your big heavy textbook? How would that affect your answers? Go ahead and pause the video and think it through. Okay, so hopefully you said something along the lines of, it would take the exact same amount of time, right? Because assuming no air resistance, assuming it is in free fall, all objects in free fall have the same acceleration. So no matter what, any object that falls from rest and falls through a displacement of 73 centimeters will take 0.39 seconds to hit the ground. And so it really doesn't matter if it's your calculator falls off your desk, your big heavy textbook that falls off your desk, your pencil that rolls off your desk, if someone is sitting on a desk and someone gets angry at them and shoves them off the desk and they fall 73 centimeters, by the way, don't do that, it's not very nice. But no matter what, any object that falls 73 centimeters in free fall will take 0.39 seconds to do so. And so this becomes sort of a bit of a running joke, at least in my classroom, that anytime anyone accidentally knocks something off their desk, we're going to say 0.39 seconds to remind everyone, oh yeah, the acceleration due to gravity is going to be the same no matter what for all objects.